Okay, I'm going to do a few sample problems here from lesson 8-1. I'll start, I think, with number 14. For number 14, we have to copy, first of all, these vectors. They have been named P and Q. One of them's red, one of them's blue. So I'm just taking my paper and tracing them. Before I trace them, I want to make sure my paper is nice and square with the page. And my paper is just thin enough that I can see through there and copy those two vectors. I'll try to get them exactly the right length and orientation. I'm going to take that over here. This one is called P, and it has its arrow going down to the left. The other one is Q, and its arrow is going down to the right. I'm going to try to take both those for my number 14 and put them on this little piece of graph paper. So first I'm going to measure how long P is. Looks like 1.6 centimeters. Now I can lay my ruler right here and do a 1.6 centimeters, but I want it to be the same direction. So I'm going to take a little piece of clear grid paper. I could use a protractor for this too, but this is a little faster. And I have that grid paper running parallel to P up there. Then I'm going to take my ruler and I'm going to start from the center of my graph, starting at the origin. I'm going to do a 1.6 down to the left, just like P does. And by having this line parallel to my ruler, I feel like I gotten that direction captured, and I measured the size, so that should be a good copy of vector P. I'm going to try to do the same thing with this other one, which they've called Q. In your book it's blue. Measuring its length, 2.5. That goes down to the right. Now this one's not going to be done from the origin because I want to add these, and to add vectors you should go head to tail. So I'm going from where the last one quit. Put my little transparency, and each student has been issued one of these, and get my ruler there. Lay my ruler parallel to the grid paper. Start a 2.5. Tilting to match Q slant. I'm going to draw 2.5 from the tip of P. 1, 2, 2.5. If you do that carefully, this P should be exactly the same as this P, and this Q should match your original Q, and the answer, the resultant they requested, will be from the beginning of the beginning, right here, till the end of your Q. So I'm going to do that one a little extra dark because it is the answer. We'll label that one R for resultant. They asked us to state the magnitude of that. I'm getting about a 1.2, I believe, 1.2. So the magnitude is 1.2. Yours may be slightly different. It's not a real exact science. That's 1.2 centimeters. They also asked for a direction. They asked for the direction relative to horizontal. So the direction from horizontal, when they say from horizontal, they're kind of talking about the way we used to do the unit circle. So straight right is 0, 90, 180, straight down is 270. So I think this one looks like it's about 40, maybe 45 degrees below straight right. So I'm going to say 315 degrees. Or you could just say 45 degrees below straight right. They just want it measured from horizontal. Again, both of those figures, you could be off a little from the answers you see in the back of the book for the odds. Don't feel like you have to nail those perfectly. Then another sample maybe I could do for you is number 20. We'll do number 20 next. That's slightly different. We're going to chart a course for a charter boat here. I'll put number 20 right next to it here. Charter boat leaves port north 60 degrees west. That and 60W means from north 60 degrees to the west. So I'm going to lay my protractor so that 0 points north, and then I'm going to find 60 direction. Oh, that's to the east. Good example of how not to do it. Lay it the other way. 60 to the west. Be off to the left on a map. So that's going to be heading out up to the left. And we want to go 12 miles. So I have to do some kind of a scale for 12 miles. I think I will let a centimeter be 2 miles. So I'm going to go 6 centimeters. Kind of running into my other problem number 14 here. That's okay. There. Put an arrow to remind me the direction. I'll put a little 60 here to remind me where that 60 was measured. That's 60 degrees west of north, that is. From north, 60 degrees to the west. And then he changes course to a bearing northeast. From north, 25 degrees to the east. So now I lay my protractor from where he is now, carefully making sure I'm looking at the grid lines so that 0 is pointing straight north. And I need a 25 degrees to the right or east. Looks like that's going to be about right here for direction. And I need to go now 15. If I follow my same scale, 15, that'd be 7.5. Shoot, going off the page. I'm going to start over. I'm going to go down here. Moving my answer down here from straight north, 60 to the west, distance of 6. Put an arrow on it. Label a 660 right in there. Put my number 20 over here. Put my protractor there. Now I have my 0 pointing straight north. 25 to the east will be there-ish. That's 25 east of straight north. So I have my 0 pointing north, and that would be the outside scale. So 25 to the east would be to the right on a map. Now I have to do 15, which is 7.5. So I'm going to go 7.5 in that direction. Yeah, now I'm staying on the paper. That's always better. That brings the boat out to here. And just to remind myself of what I did, I'm just going to put a little dotted line right there to show that that's a 25-degree angle there. This is a 60-degree angle to the west of north there. And the question is, what's his distance and direction from port to current location? I believe port's back here. Current location is back there. So a trip from port to current would look like this. So a picture of our answer would be this vector right here. I'm just going to label it port to current because I want you to know that answers the question. All we have to do is describe that vector. That vector there is the one that's port to current. We'll have to describe it, give its magnitude and direction. Its magnitude is 9.75. Times 2. That's 19.5, I think, nautical miles. I'll put a little NM after that. And the direction, I get that with my protractor. And the direction is going to be just to the left of straight north. Looks to me it's going to be about 11 degrees to the left of straight north. Straight north would be right there. And it's over here on my 79. So it'd be about 11 degrees left of straight north. The way they would write that is N11W. And 11 degrees W. So this part would be your answer then. 19.5 nautical miles at a direction of N11W. Now, just checking the answer book here, the actual answer is that. I was kind of lucky to get a perfect answer. Now I'd like to show you another way to do the exact same problem. You don't have to do them graphically. You can also do them mathematically or with trigonometry. For instance, if you know these angles, you can use trigonometry to figure out the whole triangle. This triangle that I've drawn, this angle, this side here is known to be 12. This side is known to be 15. And we need one more thing. If you remember our trigonometry, we're going to need another angle somewhere. And usually it's this angle. Since we know the orientation of these two trips, we should be able to find out the angle between them. This angle is figure outable right here. And you can kind of use the grid as a guide. If this is a 60 right down here, then this right here is a 30, and if that's a 25, you have a 30 and 25, 55. The rest of the 180 is right here. So this is the known angle of the triangle. I believe it's 125. And now you can use trigonometry to completely solve the triangle. You'll be able to find that this side is 19.5. You'll be able to find that this angle down here, using the sine law, you'll be able to find that it's 49. And that 49 will be enough for you to figure out the heading. Next, I'd like to try to do number 26. What, Mrs. Skinner?
Can I copy?
Yeah, why not?
Well, I want to interrupt your master teaching.
Oh, just go ahead. I'll speak up.
Okay.
Yeah, I'm going to do number 26. They use accelerations. You can use vector diagrams for not only distances, you can use it for speeds, you can use them for acceleration. So we're going to do an acceleration vector diagram. The geometry works out the same. We have 15 at an angle of 60 to the horizontal. So I'm getting my protractor, setting it horizontal so that I can find an angle of 60. That'd be up in that direction. And I need to do a magnitude of 15. I think I'll make that a 7.5. That's 2 to a centimeter. That'd bring me out to there. I say it would bring me out to there, but that's not what's happening. It's a speed. I mean, it's an acceleration. I can put a 15 on it though, and I can put a 60 here. And apparently, while that 15 meters per second is happening, there's also a 9.8, which sounds like gravity, meters per second going down. So I think that's should be like about a 4.9 centimeters straight down acceleration. Oops. Just to right there. So, what's really happening is an object is accelerating that way while it's falling. It would be like a rocket pointed in that direction, accelerating in that direction, but at the same time it's falling, so it ends up actually traveling in this direction. So this is our resultant, and this time our resultant isn't taking us to a place. It isn't a distance, it's a resulting acceleration. You can measure it to decide how much it is. I've got 3.8 centimeters. So that would be then a resultant of about 7.6 meters per second. And they would like to know the direction, I'm sure. So we should measure this angle. Looks like it's going up at a 25-degree angle. In a real life situation, what's happening is we have a little rocket that's pointed this way, and even though it's pointed and blasting in that direction, it's going kind of sideways because gravity is fighting it. And it is accelerating at a speed of 7.6, but it's only climbing at a 25-degree angle. So that's a nice example of how these vector sketches and calculations can be used for more than just distances, as we did in our trig triangle chapter. Then I think I'll do one more here, maybe number well, first I want to make a comment about number 35. In 35 it says a runner's velocity is, his resulting velocity is 8 due west. That's how fast he's running with a 3-mile-an-hour wind. So then they're asking you what his speed must have been without wind. I think that's kind of dumb. If you do any track at all, you probably realize that the wind doesn't exactly add to your speed. So I'd like you to do this problem like it's a bird instead of a runner. I'm telling you, a 3-mile-an-hour tailwind does not add 3 miles an hour to your speed. Then let's jump to maybe 38. Do that down here. On 38, we have to do a 2 1/8 inches at a 310 degrees. Well, the direction for 310 from the horizontal, again, if they're measuring from the horizontal, they're kind of doing it like the unit circle. So straight right is 0, straight up is 90. 310 is going to be down to the right, like a 50-degree angle down, sort of. So I'll get that little aiming spot right here. And I have to make that 2 1/8 inches long. Oh, that's just gonna fit. 2, using the inch side of my ruler. That is the vector, and they want us this time to resolve it into horizontal and vertical components. That means they're asking how much right and how much down is a 2 1/8 at a 310. Well, that's pretty easy on a grid here. It looks like you can make a nice right triangle, just like so. And this is the horizontal component of the vector. I merely need to measure it. It is 1 3/8 inches. Right. And the vertical component is 1 1/4, 2/4, 5/8. 1 5/8 down. That's what they're wanting you to do when they say resolve into components. You break a slanted vector into 2 components at a right angle that would make the same thing. That should be enough of a start for you to be able to get some of the harder ones on this assignment. At least you should have these. See you tomorrow.